Welcome to the cardiovascular function during exercise simulation. In this simulation you will perform stress tests on humans to see how the cardiovascular system responds during exercise. You will also learn a method for preliminarily diagnosing one type of heart problem. Click Continue to start with your mission. The human body is a very complex system, and when exercising, many different processes occur at the same time to help the body supply enough oxygen to meet an increased demand. Not only does the heart beat faster, but many other compensatory mechanisms optimize the transport and use of oxygen in the body. Before we dive into different cardiac mechanisms and parameters, first we need to understand the basics of the heart. Let's learn how it works. Click on the mini-pod by the sink to teleport to the heart scene and learn more about the heart. The human heart has two chambers located to the top of the heart. They are called atria. You can see them highlighted. Below the atria, there are two other chambers. They are called ventricles, and you can also see them highlighted. Oxygen-poor blood comes into the heart through the vena cava into the right atrium. When the right atrium is filled with blood, it contracts and pumps the blood towards the right ventricle. Once the right ventricle is full, it contracts and pumps the blood through the pulmonary artery towards the lungs. In the other side of the heart, oxygenated blood comes into the heart through the pulmonary vein and follows a similar route than blood at the right side of the heart. Blood goes from the left atrium to the left ventricle, and then, to the aorta, which distributes oxygenated blood to the rest of the body. Let's see the movement of the heart all at once. Well, now that we know how it works, we can go to the lab to start planning our experiment. Pick up a lab coat from the rack. Well done. Now find a glove box and click it. Let's clarify some concepts about the circulatory system to better understand all the processes that are happening. Click on the wall screen. Heart rate is the number of times the heart contracts per minute. The primary pacemaker of the heart is located in the upper part of the right atrium. The average heart rate of a person at rest is between 60 to 70 beats per minute. Stroke volume is the amount of blood pumped by the heart in one single beat. This volume is dependent on the volume of blood returning to the heart and contractility of the ventricle. Average resting stroke volume is roughly 70 milliliter per beat. Click on the screen to learn about cardiac output. Oxygenated blood leaves the heart, traveling through the aorta which branches off into other arteries that carry blood throughout the body. The volume of this blood is called cardiac output. It is the product of heart rate and stroke volume, and it is, on average, 5 liters per minute at rest. Blood flows through the circulatory system thanks to the pressure generated by the heart, so it is pulsatile. The maximum pressure happens right after the left ventricle contracts and it is called systolic pressure. The minimum pressure happens right before the left ventricle contracts and it is called diastolic pressure. Blood pressure unit is typically millimeters of mercury. During exercise the muscles require more oxygen, and consequently, the heart responds by pumping more oxygen-rich blood. The oxygen used by the muscles can be calculated by multiplying cardiac output times the difference in oxygen concentration between the venous and arterial blood. This graph represents the average increase in oxygen consumption with increasing exercise intensity in humans. How much does the oxygen consumption increase with exercise intensity before it plateaus? Exactly. When we increase the intensity of the exercise, the oxygen consumption rate increases proportionally until it reaches approximately 8 times the baseline and then it plateaus. Now that you know how much oxygen consumption increases, I am going to ask you to make some predictions about other variables. You can do it. If oxygen consumption rate increases 8 times, how much do you think the cardiac output will increase? What about heart rate? And stroke volume? And diastolic blood pressure? Perfect. Thanks for all your predictions. We will come back to them at the end of the experiment to see whether they were right or not. Now it is time to start our experiment. Remember that we want to see how the cardiovascular system behaves during exercise. I have collected all the information needed to run the experiment. Click on all 4 different areas on the screen to obtain information about the experiment. The experiment will be conducted on 5 female and 5 male individuals. All of them have volunteered for the experiment. You will only need to follow the procedure for one of the individuals. I will take care of the rest. The individuals will have to exercise at 5 increasing intensities that range from 25 to 125 watts. Exercising individuals will use a cycle ergometer, which is a stationary bike that allows us to regulate the intensity of the exercise. Each exercise period will last for 6 minutes. It will be followed by a resting period of 5 minutes at the beginning and increasing up to 15 minutes at the end. The total duration of alternating exercise and rest periods per individual is 69 minutes. Well, now that we know how we are going to execute the experiment, we should learn how to measure the different variables of interest, such as heart rate, cardiac output and stroke volume. To measure all those variables we can use the Doppler ultrasound device. It is based on the Doppler effect. How convenient. What is the measurement of the velocity of moving particles the Doppler effect is based on? Spot on. The shift in the frequency of the sound allows us to measure the velocity at which those particles are moving. Isn't it amazing? Look at who is coming into the lab. His name is Frankie. He will be our first study subject and he is completely healthy. We should start by measuring the different variables at rest on him. Let's try to use the Doppler ultrasound system to measure the different variables.
I am really excited about taking part in this experiment. I am ready to start as soon as you tell me.
Pick up the transducer from the base of the ultrasound machine. To measure the desired variables we need to do it from the aorta, so we need to point our probe towards the aortic valve. To do so, we need to find the exact right spot on the patient's neck. We can use the model of the patient's head on the hollow table to your left to see possible locations more clearly. The right area is called supraclavicular fossa area. If you choose the correct location you will see a pulsatile signal. Click on one of the highlighted areas on the head on top of the hollow table to start measuring. Do you think that the measurement was accurate? Yes, this is a clear pulsatile signal and the values of heart rate, stroke volume and cardiac output look reasonable for a healthy human. We can use this data. As you can see, the device has calculated the variables for us, taking into account different factors. You can see this on the screen of the Doppler ultrasound machine. Thanks to the Doppler effect we can calculate the velocity at which blood is moving through the aorta. Once the average velocity over multiple heartbeats is known, what other parameter is required to calculate the cardiac output? Exactly. If we want to calculate the cardiac output we need to know what is the surface area of the aorta. We can get that information from previous studies, since it is related to the person's height. I will save the data from the patient. Now we can move on to the next variable. Put the transducer back on the workbench. To measure blood pressure, we use an aneroid sphygmomanometer. Let me show you how it works. Before we inflate it, the blood flows through the brachial artery normally, and we can't hear any sound using the stethoscope. When we pump air into the cuff until the pressure reaches about 180 millimeters of mercury, we interrupt the flow of blood. When we let out the pressure slowly while listening to the stethoscope, we will hear a knocking sound at the same time that the needle of the sphygmomanometer will bounce up. That is the systolic pressure. This happens because blood is spurting through the blood vessel during the short time that the pressure in the artery is higher than the pressure in the cuff. From now on, the needle will go down but it will bounce up and down each time blood spurts through the vessel. Additionally, the sound in the stethoscope will be more and more subtle. At the pressure when the needle stops bouncing, and the knocking sound fades, that is the diastolic pressure. At this point, the pressure in the artery always exceeds the cuff pressure, so blood flows smoothly through the open artery. That was a lot of theory. Let's try to measure it on our test subject. It's easy, I promise. Move to workbench 2. Here's Frankie again. Let's set the sphygmomanometer and the stethoscope to start measuring. Place the sphygmomanometer on the patient's arm. Place the stethoscope on the patient's arm. Pump air into the cuff until it reaches 180 millimeters of mercury. Good job. The pressure is up to 180 millimeters of mercury. If you click on the pump now, it will release the pressure little by little. Remember that, for the systolic pressure you need to pay attention for the first knocking sound and needle bounce up. For the diastolic pressure you need to pay attention to the moment when the sound fades and the needle stops bouncing. Did you get both of them? If in doubt you can click on the pump again to increase the pressure in the cuff and repeat the procedure. Did you get both of them? What is the correct systolic and diastolic blood pressure of the patient? Exactly. That is completely right. You can definitely identify blood pressure. We just finished measuring both variables at rest in one of the patients. This could take a while to perform in all patients. Did you think that you had to measure it every single time in all the subjects? No worries. We are in a virtual lab and we can do it really fast. Give me a bit of time and I will run all the remaining tests for you. Click continue on the lab pad to fast forward time 1 day. We are done with the measurements. You have all the data on the big screen in the lab. Let's go analyze it. Have a good look at all the data. Take into account that you can switch between the different variables using the tabs on the top of the screen. We need to check whether your previous predictions are correct or not. You predicted that heart rate would increase by 8 times comparing the values at the maximal exercise intensity to the values at rest. How did it change in patient A? That's right. You have a sharp eye for data. You predicted that the stroke volume would increase by 8 times. How did it change in patient A? Another one right. You really rock. You predicted that the cardiac output would increase by 8 times. How did it change in patient A? Boom. Another right answer. You are on fire. Given that cardiac output did not increase as much as the oxygen consumption rate, what is the most likely mechanism that could allow increased oxygen delivery by the cardiovascular system? Precisely, when more oxygen is needed by the muscles, and the cardiac output can no longer increase, the body starts to increase the amount of oxygen removed from hemoglobin. That can be seen as an increase in the difference of oxygen content between the aorta and the vena cava. Seems like you have mastered the cardiac variables. Now we can move on to the blood pressure data. Notice that the tabs for the blood pressure data are now available on the big screen. Here you have systolic and diastolic blood pressure data from all patients. You predicted that the diastolic pressure would increase by 8 times. As stroke volume increased by nearly 2 times and cardiac output increased 4 times with exercise, how did diastolic blood pressure change in patient A? And right on again. It seems like you are never wrong. In fact, diastolic pressure didn't increase much. A very useful parameter that can be calculated with systolic and diastolic blood pressure is the mean arterial blood pressure. It can help us to compare blood pressure among different subjects. Let's see how we can calculate it. Move to workbench 2 and look at the PC screen there. Here you can see the formula that is used to calculate the map. Let's calculate it for our data at 125 watts and at rest. Fill the right numbers in the drop-down menu for subject A in the PC screen and press confirm to check the results. You can find the information on the wall screen. Exactly. Seems like diastolic blood pressure didn't change much between rest and 125 watts. However, systolic blood pressure did increase, and that made the map increase from 83 to 105 millimeters of mercury. What is the most likely explanation for such a low increase in the mean arterial pressure compared to the cardiac output? You are a genius. Yes, one of the hallmarks of exercise is that the arterioles and capillary beds supplying the exercising skeletal muscles vasodilate, allowing more blood to flow to these tissues that need the oxygen. The increase in systemic vasodilation causes a decrease in the total peripheral resistance of the circulatory system. TPR can be defined as TPR equals mean arterial pressure divided by cardiac output. For subject at rest, MAP equals 83 mm of mercury and CO equals 4.2 liters per minute. For subject at 125 watts, MAP equals 105 mm of mercury and CO equals 18.0 liters per minute. What is the ratio of TPR at rest and TPR at 125 watts? That's right. When we exercise, our arteries and arterioles dilate, so they offer less resistance to the blood flow. In case you didn't realize yet, Subject D was unable to finish the exercise at high intensities, and he had a hard time with some of the medium intensity ones. Let's learn a bit more about the valves regulating the blood flow in the heart. That will maybe help us understanding what happened with the last subject. Click Continue on the lab pad to teleport again to the heart scene. Let's learn about the heart valves. Let's follow the movement of the valves during a heartbeat. The atrioventricular valves open so the blood can move from the atria to the ventricles. The one on the right is called tricuspid valve and the one on the left is called bicuspid valve. When the ventricles contract, the atrioventricular valves close to prevent backflow of blood into the atria, and at the same time, the semilunar valves open to allow the flow of blood out of the heart. The left semilunar valve is called aortic valve and the right is called pulmonary valve. Finally, when the blood has already passed, the semilunar valves close to avoid blood backflow. Now that we know how the valves work, let's see if you can point out what was different with the data from the last subject. Let's head back to the lab. How did the measured cardiac variables differ in subject D from the other individuals? You can check the data on the big screen in the lab. Exactly. Subject D experienced higher heart rate, lower stroke volume and diastolic pressure and a higher systolic pressure. With all this information, it seems like something may be wrong with Subject D's heart. Which of the issues below aligns with the data from Subject D? You can check all the data on the screen and the theory pages to get some help. Exactly. When the aortic valve fails to close, part of the blood pumped into the aorta flows back into the ventricle, reducing stroke volume, cardiac output and diastolic pressure. This increases the amount of blood in the ventricle, which makes the heart increase the force of contraction, causing higher systolic pressure. Good job. Definitive diagnoses will require some direct visualization of the valves, but Subject D should definitely be referred to a cardiologist. We have tentatively diagnosed the patient with a failing aortic valve, and hopefully saved his life. Additionally, we have learned on the way how the different heart parameters change when exercising. Congratulations, you have completed the simulation. We hope you enjoyed it and you feel wiser now. Press exit to close the simulation.